Good day, everyone. Today I'm going to speak with you about nucleophilic addition to polar pi bonds. So this is going to be a two-part series. The first, today we're going to really discuss nucleophiles that amend to electrophiles. In other words, different types of electrophiles you'll see here that are carbonyl based, as well as nitrile. Oops. And even alpha beta unsaturated double bonds. Okay, so this is a particular ketone species. All right, but in particular, the nucleophiles that we're going to be using to amend onto these carbons containing polar pi bond, constructs are going to be charged. Okay, so they're going to be strong, in other words. Okay, so it's going to be an electron-rich species going to each one of these carbons that are going to be electron poor, right? Because this electronegative atom is drawing electron density away from those particular carbons to which they're amended. Okay, so let's go over some electrophiles you're going to see in this chapter, that being chapter 17. So the first is going to be aldehydes. Okay. And then you'll also see ketones. So that's an alpha beta unsaturated ketone. So the unsaturation's right here between alpha and beta here. So okay, and that's a nitrile. Just simple ketone here. Let's just say take acetone. Okay, and then you'll also see imines, or what are referred to as shift bases. Okay, so our group could be either hydrogen or carbon of some kind, right? So that could be an alkyl group, an aryl group, what have you. Okay, the only one that has any type of stereospecificity is actually going to be this type of group, which again is going to be an imine or shift base, I may refer to it. Okay. Now, as stated previously, all these carbons are going to be activated based on their electronegative group that's directly attached to them with at least one pi bond here. So notice here with nitriles how you see there are a total of 2 pi bonds, so this is going to be a linear construct. So something to think about also, if you think about reactivity, certain types of electrophiles like you see right here are going to be more reactive than others. So in this case, for instance, with nitriles and aldehydes, a carbon on a nitrile is going to be in a linear construct. So in other words, either side is open to attack, right, from a nuke. And then for aldehydes, it's a little bit more open with just hydrogen on one side, right? But there's kind of a 50-50 probability of going into or out of the plane of the page board as it is right here. But remember also this is going to be planar, right? So it's going to be sp2 hybridized. This is going to be sp hybridized. Now, one thing to think about in terms of nucleophilicity, just as a review, is the stronger nucleophile is usually going to be the charged nucleophile. So in other words, I had some sort of a review exercise for you to do to place an order of least to most nucleophilic strength. You also have to think in terms of what kind of solvent. So it's solvent dependent. Okay. So for protic solvents, larger nuclei, or the larger the nuclei, better nucleophile. Okay, and then the opposite. So, for instance, let's say if we're comparing SH minus versus OH minus, right? They're going to be isoelectronic because they're going to be about the same group 6A, but that sulfur is going to be able to stabilize that negative charge rather than OH. So OH is going to be more compact. It's going to be more electronegative, right? So in an aprotic system, it's going to be a better suited nucleophile versus in a protic system, right? Because that OH can also participate in hydrogen bonding and things like that. So if a protic solvent is there, and there's going to be some kind of interaction with that, and it's going to weaken its nucleophilic capability. Okay. So that's just some things I wanted you to think about, because you're going to see some examples in this chapter where it's going to be, aprotic as well as protic. Not, of course, combined, but, depending on what type of particular conversion you're going to be doing. Okay. So, let's go with the first example here. So this is, say, a strong base nucleophile like CN minus. So CN minus is just nitrile with C and N with a lone pair about the carbon. So we'll react that with, say, an aldehyde. And it's going to form what is referred to as a cyanohydrin. So so we have a planar species. And one thing I've noticed, when you do these kinds of additions, and it's not one of these addition elimination reactions, it's just an addition, you will see that you're going to go from 2 dimensions to 3 dimensions, right? So this is an sp2 carbon with that amending nitrile. That's going to be sp3. Okay. And I wouldn't stop right here, because you would need to acidify that in order to have an organic compound, so you would just use an acid workup for a second step. Of course, if you use an acid workup while you were trying to add this, what is it going to do? It's going to protonate this, because this is also a base. So it has to be under basic conditions before you can kind of proceed. And again, this is going to be the workup stage. So forming a cyanohydrin here again. So cyano from this nitrile group, okay, and then OH from for the hydrogen. So this is again cyanohydrin. Maybe last semester you remember synthesizing or creating a functional group called a halohydrin. So instead of that hydroxyl group directly amended to a carbon that has the cyano group here, you would have maybe Br or Cl hanging off of the adjacent carbon to it. Okay, so also a thing to consider is that if you're attacking this sp2 group, just think about it just the same way you would think of, let's say, a tertiary carbocation, right, that is stereospecific. So, you know, you have a 50-50 shot of hitting either side. So, in other words, you're going to get a racemic mixture. Okay. So, usually when I draw a racemic mixture, I tend to put this sort of squiggly line to indicate that it's going to be either R or S 50%. Okay. Okay, so the general trend, if we're just comparing some electrophiles here, in terms of reactivity, formaldehyde is going to be most reactive, followed by say acetaldehyde, and then acetone. Okay. Even lower on that sort of totem pole is, or order, if you will, is going to be an aryl, or let's say diphenyl ketone, like what you see right there. Reason being is because these phenyl rings are also withdrawing electron density from that particular carbon. Now there's going to be sort of resonance stability throughout there, right? It's all part of one larger sp2 construct. Whereas right here, these two carbons that are on the wing are both sp3. Okay, so there's no resonance stability here. Also, as you get to more access, in other words, when you have hydrogens in lieu of these CH3 groups or the phenyl ring, you're going to have more access. So in other words, as you get bigger and bigger groups, of course, it's going to become more sterically bulky, and that particular carbon is going to be less accessible. Okay. So let's take a look again at Grignard reagents. So Grignard reagents reacting with some kind of carbonyl, like what you see right now, is going to generate a secondary alcohol, or even tertiary alcohol if you're talking about a ketone. So aldehydes are going to generate secondary alcohols, and ketones are going to generate tertiary alcohols. So we'll go over the example in the notes that I provided for you. So it's divergent, right? So there are two different functional groups that you're reacting. So the first is going to be, so this one's a ketone to tertiary alcohol. Okay. Okay, so the first step, you're just going to introduce your electrophilic substrate, which is 2-pentanone. I'm going to take that lone pair, which is going to be highly reactive, bump right here onto that carbon, that electrophilic carbon. And this pair of pi electrons jumps up to the oxygen, where the charge can be stabilized. And then okay, so this is going to be an irreversible step, right? So in other words, this is a really terrible leaving group. Okay, so tertiary alcohol, once again, 1, 2, 3 carbons directly attached to that carbon where that alkoxide anion is. It's going to pick up hydrogen plus from that second step. Okay. So this is the first step, and that's the second step. So again, if you had hydrogen or H plus available on the first step, what's that going to do? It's going to render your Grignard reagent unreactive, right? Because if it's a strong nucleophile, it's also a strong base. Okay. So again, tertiary alcohol. All right, let's wear the shoe on the other foot with the same nucleophile, but this time we're going to react it with this particular nitrile. Okay, so again, we're going to attack the electrophilic carbon there, bump these electrons up. I didn't mean that to look like a fish hook. There you go. Okay, so notice how I mentioned earlier that you're going to go from an sp2 construct to an sp3 carbon. Same goes here. Instead of sp, you're going to go to sp2. Okay, so you'll have the negative charge out that nitrogen. So 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Okay. 1, 2, 3, 4. Cross that off. Okay, so treating this really with H3O. Right. So remember that H plus is really just a shorthand for H3O. That oxygen is going to wind up in place of where that nitrogen is. So what you're really going to get is a ketone. It's going to be most stable. Okay. All right. So again, there's going to be an acid workup for the second step. All right, so let's predict some products from problem 17.36. This is on page 881 in your text. Okay, so B and C. First one, you're going to react a cyclic ketone with KCN. So remember that KCN is the conjugate base of hydrogen cyanide. Again, B and C are going to be the two examples I'm going to go over with you. Just kind of reviewing what was in the beginning here. Okay. So there's no stereospecificity, which is a good thing. Kind of keeps things a little less complicated. Okay, so you have this in water. Oops. Too many O's. Okay, so there's that CN minus is going to act as your nuke. Again, bump these electrons up. Don't have a full octet, still about that carbon. Now that oxygen has a negative charge. You have that CN amended. And this is going to be quite basic, so it's going to pick up a hydrogen from water. Oops. Okay. And then you're going to have your cyanohydrin, your non-stereospecific cyanohydrin. Again, because there's symmetry about the ring. Okay. So again, that's just cyanohydrin formation. Pretty straightforward. Okay, for B, you have looks like this is your nucleophile in the presence of ethanol. And then we have an aldehyde as our substrate, which is again going to be rather accessible. Remember, I also said earlier that if you have a protic system, something like sulfur is going to be better suited. The larger atoms that have the negative charge are going to be better suited as nucleophiles. Okay, so in this case, it's going to be a good nuke. Also, if you want to just look over or kind of review some of that theory, you can go into chapter 9, I think it's 9.6 in your text, and take a look at sort of the comparison between protic and aprotic solvents and nucleophilicity. Okay, so we're going to bump these electrons up. Okay, we're going to have our anion as a result. So again, you're just following charges, really. So you're following a negative charge here, right? Because everything's going to be under basic conditions. Okay, so now this is just going to pick up a hydrogen from your ethanol, i.e. your solvent, just like part A, or sorry, part B rather. Okay, so that end product is going to be a racemic mixture. Just keep that in mind. So I'll just say that that OH is going to be squiggly lined. Okay. Again, that's just a shorthand that it could be R or S, flipping either way. Okay. So pretty straightforward. Again, going from sp2 starting material to an sp3 carbon product. All right, so now we'll get into some reducing agents. I've kind of introduced these to you a little earlier in the semester. So I did speak about sodium borohydride, but I'll also introduce lithium aluminum hydride, which is going to be a little bit stronger. I'll explain why here in a minute. Well, let's go through some examples here from figure 3 in your notes. Okay, so the first is going to be this aryl alkyl ketone. So sodium borohydride is going to look like this. So this is going to be the first step. Notice how there's 2 steps. Remember that each one of these numbers is going to indicate that that's sort of a physical separation in terms of the introduction of your, so it's like an order in which you add these particular reagents, right? So if you added water and H2SO4 to sodium borohydride, it's going to render the sodium borohydride inactive because this is going to be conceptually basic, okay? All right, so you have sodium plus, so that means you have to have a counter ion. So borohydride is going to be like so. Okay, negative charge there. So just a quick back of the envelope calculation. Boron has 3 electrons in the ground state, valence electrons that is. Okay, and we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2, no lone pair electrons, so that's going to leave us with a -1 charge. So that's where the formal negative charge is. So what actually occurs is that one of these hydrides, or H minuses, essentially, is going to attack right there and kick up this electron, or set of pi electrons. Okay, so effectively this is H minus. Okay, so H minus is going to be different than sodium hydride, which we'll get into in a little bit, because sodium hydride is an irreversible base. It does not behave as a nucleophile. So in other words, this Boro group is really trying to drop that H minus like a hot potato, right? So if it bumps up these electrons, so in other words, this is reducing that carbon-oxygen double bond to form an alcohol. So the second step is when you introduce your H plus, right? And these lone pairs are just going to pick that up at will. Remember that proton transfer is going to be one of the faster things that happens mechanistically. Okay, so now we have OH here, so we're done. But also remember that since we started off with a planar substrate, we're going to have a mixture of R and S. Okay? So it's, again, something else you want to think about. You can try the second example that I have here on the notes. I'm sure you'll come up with something very similar. But we're now going to get into lithium aluminum hydride. Okay, so lithium's here, lithium plus. So it's going to be analogous to this, isoelectronic in other words. So aluminum is also in group 3A. So all this stuff is in the main groups. Okay, so lithium is going to be a little bit more electropositive. And then the difference between lithium and aluminum, right, as opposed to sodium and boron, is that this is going to be a greater dipole stretch, right? So while both of these are classically ionic compounds, this one is going to be a little bit further polar than your sodium borohydride. So this is going to be more reactive as a result. Okay. So this is actually going to reduce nitriles and also reduces imines to primary or secondary amines. Okay, so in other words, if you were to treat, let's say, let me erase some of this junk on the top here. Let's do it formally. Okay, notice for the second step, you just need water. Right, because what's going to happen is you add more hydrogens here, it's going to kick some negative charge up to where that nitrogen is, and those electrons are going to become even more basic. Okay, so the overall transformation here is not going to happen once but twice in terms of reduction, and you're going to get primary amine as a result. And then for the imine, which we'll get into imines in a little bit here, but let's say you have this particular imine. I'll just write pH here. This should be in figure 4, by the way, in your text. Or sorry, not in your text, but in your notes. Okay, so once again, I'm going to kind of earmark these hydrogens to tell you where they end up. So we'll say lithium aluminum hydride, put the $sign there, right, to indicate that that's where those particular hydrogens wind up. Okay, but they're going to be different species of hydrogens. This is going to be H minus. This is going to be H plus or protic. Okay. Same goes with what you see here. Okay, so by adding 2 hydrogens onto here on each side, that means it's going to be non-stereospecific. Alrighty. So once again, $sign for the earmark for where the hydrides are going, and then asterisk for earmarking where the protic hydrogen is going, which is right here. So remember, you started off with an sp2. Now you're going to wind up with an sp3. Again, this is going to have some freedom of rotation, non-stereospecific from either of these particular carbons having methylene identity. Okay, so now we're going to revisit carbon-carbon single bond formation. You've already seen that with Grignard reagents. So we'll introduce some other organometallic species that are going to perform similar bond formation, as well as some that may form carbon-carbon double bond formation, such as Wittig. So one thing I want to sort of stress, this is something you're going to do from a practical standpoint, is that all of these are dangerously reactive. Okay, so that's why carbon-carbon bonds are such a sort of a sought-after, I guess, tool in organic chemistry. Seeing is that it needs some pretty powerful electronegativity if you want to skip sort of steps, if you will, in forming those particular bonds. But there's some ways in which you can get a little bit ahead of yourself and have things render themselves inactive. Okay, so this is sort of a synthetic trap that I'm going to show you here. So Grignard or some alkyl lithium reagents shouldn't self-react. So a couple examples that I'm giving here in figure 5. Okay, so let's say the Cl group. Okay, so everything's good and dandy up there if you were to wedge in a magnesium, right? But in the diethyl ether system, However, you have a very reactive electrophile functional group just below it. So in other words, this would effectively polymerize, right? So or self-react. Okay, so that's going to be an issue right here. Right? Because if you let's just think from the standpoint of molecule to molecule, right? Maybe over okay for the first example, but then you have another molecule that's right next to it, right? So that is going to be what is referred to as labile. Okay, in other words, reactive. So that's going to be a pickle, a jam. Okay, so let's take another example here. Maybe something that's a little bit less obvious. Okay, so treat this with elemental magnesium and diethyl ether. So this is an aprotic solvent. That's seriously by design, because when you form your Grignard reagent here, and I'm going to do that, what does this also behave as? Strong nucleophile, also a strong base. Okay, so if we have, say, another substrate here, or sorry, nucleophile we're trying to form here, and it has that OH right there, a couple things are going to happen. One, a lone pair is going to pick up that hydrogen, rendering it, that particular Grignard reagent, inactive, but also these electrons are going to come cascading down and boot this bromo group off, and you're going to have a more stable ketone. Okay. So pay attention to what type of substrate you can use in order to wedge in that magnesium and have it not self-react. That's really the main message there. Okay, so let's look at another example with alkylithium. So we'll do a full mechanism here. And alkylithium reagents are typically made with an alkyl halide and then reacted with elemental lithium and THF. So in figure 6, I've already prepared the alkylithium reagent for you, but treat this with Li, again in the ground state, substituted version here. All right, so it's going to be a salt that'll be reactive. Okay, so then you would introduce your electrophile, which is just going to be acetaldehyde. Okay, so this isn't going to be protic, right? So it's not going to strip off that hydrogen. What it's going to do is actually react right there at the electron depleted carbon. And as a result, you're going to get an sp3 hybridized carbon. Okay, and then the second step, you're just going to introduce some acid. H plus, H3O, same difference. It's going to pick up that hydrogen, and then you formed a secondary alcohol that's going to be, once again, R and S mixture, right? So again, you're starting with an sp2 substrate. Okay, so let's go over a couple of examples in your text on page 882, problem 17.47b and 17.48b. So I'll draw both of those on the board here. This is 17.47b. Aldehyde. Treating that with an alkylithium reagent, looks like butyllithium. And then a weak acid workup. So what's happening here is that lone pair, again, attacks the electron deficient carbon. I'll erase this up above. So get a product here. Hanging off this naphthalene ring is a secondary alcohol, a few carbons removed. Again, mixture of R and S here. That's a hydrogen, by the way. It's not a nitrogen. So let's see, 1, 2, 3, 4. So 1, 2, 3, 4. And there you have it. Okay, 17.48 B. Okay. Next example down. So we have an imine. Put pH right there. Put pH right there. Remember the lone pair that's attached to that nitrogen. Okay. So the first step has the same nuke. That positive charge there to remind you that it's a salt. Okay. And 2, it's introducing ethanol. Okay. Which will make more sense here in a second. So remember, for the second step, you need a weak acid to acidify and work up that alcohol from the alkoxide anion. So remember, the anion occurs from this pi bond, these two pi bond electrons getting kicked up towards the oxygen to give it a formal charge. Okay, so the same thing's going to happen here about this imine, right? And the imine has a negative charge, the nitrogen anyway. One, two, three, four. Good. Okay, so this is also going to be a 50-50 mixture. Again, because you have 4 different coordinates about this particular carbon here. So this is just going to pick up hydrogen from ethanol. Okay. Then you're going to have your racemic mixture products. Okay, so now we're going to get into carbon-carbon double bond formation. The first approach I'm going to show you is Wittig. And in the next couple of submodules, you'll see that you can use something that was referred to as Grubbs catalyst for a disproportionation sort of reaction or a metathesis reaction between 2 terminal alkenes. Okay, but in this particular case, you're forming a carbon-carbon double bond from a ketone, sort of like how we're used to here already. But just before we were doing carbon-carbon single bonds. Okay, so let's take this particular substrate that I introduced to you in figure 7 of the notes. Okay, so first step is, I'm just going to go through this in gory detail for you. You have triphenylphosphine. Okay, so 3 phenyl groups attached to phosphorus. And phosphorus is the nucleus that's going to attack. So, in effect, it's going to kick off this bromo group. So there's going to be an additional hydrogen here. Don't forget about that. Okay, so away Br minus goes, or at least it stabilizes the charge that impends. It is impending, rather. Okay, so that phosphorus is going to have a positive charge right there. That positive charge is going to pull electrons away from that carbon-hydrogen bond to render this hydrogen more acidic. So the second step is when you introduce N-butyl lithium. So N-butyl meaning natural or linear. Okay, so this is going to act as a base. And these electrons are going to go up. Sorry, they're not going to go up, rather. They are going to actually be a zwitterion. So your W's and V's are kind of in an upside down world, kind of like Australia, right? Okay, so we have a zwitterion, meaning that, and that's ZWITTERION. So you have a negative charge here, a positive charge here for net neutral. Okay, and this is a Wittig reagent, so there you have it. Okay, so this Wittig reagent that's been prepared here from these 2 steps. Again, first introducing triphenylphosphine to this particular alkyl halide. One other thing to note here is you need at least this hydrogen, so it needs to be secondary at the most in terms of carbons attached to other carbons. right? So it needs to be secondary or less. So right here, you're going to react with some kind of carbonyl species. So we'll introduce the carbonyl here. And how is this going to work? Well, we have a nucleophile here, and it's going to push these electrons up. And this lone pair, remember, that's going to induce a negative charge. These electrons are going to come up and coordinate with that electron poor phosphorus. Okay, so it looks like a big old jumbled mess, but have no fear. We'll have an intermediate here that'll quickly resolve itself. Okay, so we're going to have a four-membered ring. Oops. So as you can imagine, phosphorus, which has a valence of 5, is pretty much at capacity here. But oxygen kind of does want its electrons too, right? So we have now yeah, 1, 2, 3. Okay, so we'll put that methyl group down there. Okay, so this is the 6-membered ring we were originally working with. Now everything kind of cascades off like so. So by these electrons flipping down, we have a full octet everywhere with the exception of phosphorus, because phosphorus is going to have an expanded octet. But we're going to form now this is a byproduct, and then we're going to form this tetrasubstituted alkene. Okay. As your product. So it seems pretty involved, but once you see PPH3 and then, N-butyl lithium, you'll know that it's going to be a Wittig reaction. Again, you need to start off with some kind of alkyl halide there. Okay. So this next exercise is something I'm going to slowly kind of introduce you to, which is retrosynthetic analysis. So you're going to be able to identify where a bond like this would be established. Okay, so this would be a product, looking back on how you would form that particular product with two reactants. So let's look at problem 17.56, A and C on page 883. I'll put those up right here. Okay, so for A, we have phenyl ring here, here, so it's about a transalkene. So it's going to be a little bit more difficult to make an form an alkene bond and make benzene. So I think there are easier ways to go about it. So in other words, if you're to do a disconnection, it would be right there in between the CC double bond. That again isn't part of a lower energy, more stable ring. Okay, so in other words, one side is going to be, let's say, an aldehyde, right? Because you need that hydrogen up there. And then the other side is going to be, let's say, benzyl bromide or something like that. Okay. All right, and then C has tri-substituted. So this is di-substituted. This is going to be a tri-substituted alkene product. So again, you're going to want to chop up that alkene right here. Okay, so stemming from that, you would have, let's say, acetone. And then you would have benzyl bromide from that. All right, so the last thing we're going to cover in this module, or submodule rather, is conjugate and direct addition. But the first thing I want to go over with you is reversibility. Okay, so if you look on page 865 on the bottom right, you'll see table 17.2 or -2. So you can kind of see it divided up into what's going to form a bond with particular carbon substrate, either reversibly or irreversibly. Reversibly usually takes some kind of electronegative moiety as opposed to carbon. So carbon or even hydrogen itself can kind of stabilize something and have it amend irreversibly. So we'll go over some examples here with the same substrate. Okay, so this is figure 8 in your notes. Okay, so I deliberately just drew a regular old ketone. So KCN, as you know, is going to amend right here and boot these pi electrons up to where the oxygen is, so the charge is going to be conserved throughout. Now this is going to be a reversible process, right? So that Cn minus could get kicked off in some way. In other words, if you were looking at an energy diagram, those energy levels would be somewhere close by between reactants and products, right? Same goes for, let's say, methoxide anion. Right. So I have sodium here as a counterion. Again, this will also attack in the same method. OCH3 can, while not the world's greatest leaving group, can also kind of revert back to breaking from that particular coordination. Right, so in other words, when this alkoxide anion is generated, there's a possibility for this lone pairs to come back down and reestablish that double bond. Okay, and then kick off, quote unquote, some kind of leaving group. So that's really the basis of reversibility. We're not talking about, a way in which you can undo what you did or undo what has been done chemically, right? More so of what's actually happening in the reaction in the situation. So an irreversible example is, say for instance, if you took a methyl Grignard, right? So that first step is going to be irreversible, right? With that said, that alkoxide anion, while we do have 3 carbons, so in other words, this is going to be a tertiary alkoxide. You'd think that all that inductive effect would kind of destabilize that negative charge, but in fact that's just going to make this O- more basic. So again, onto the second step, you're just going to acidify, right? So all these second steps, you're going to have some acidification either through the solvent or by some other means, okay? So the top 2 are going to be reversible, again, because you're going to have some electronegative species that are going to amend directly to that CO double bond. Or about that carbon that's part of the CO double bond, rather. Okay. So if we take a look at 17.59 on the bottom of page 883, we'll go over, let's say 3 or 4 examples here. So 17.59. So let's go with F. Okay, so this is going to be a bulky substrate. Oh, excuse me, this is a conjugate base of that. So this is actually going to be better suited as a base as opposed to a nucleophile, but it's going to be reversible technically. Okay. Again, since that business end, that negative charge is going to be about that nitrogen that's going to amend to the carbon. Okay, so let's say, let's take another example, J here. So J is conjugate base of a thiol. Okay, so sulfur, again, is going to bump into this carbon or some kind of CO double bond, and there is going to be some reversible. So it's going to be reversible, reversible. Okay. How about E? So this is an lithium cuprate reagent. Oops. Well, I'll just draw it like so. Okay, so you're going to have 2 particular alkyl groups. I'll get into lithium cuprate reagents relatively soon. But you have 2 propyl groups that are effectively acting. One of them is going to be behaving as a nucleophile. Okay, so with that bulk, remember that you have a carbon that's going to be directly amending to that particular substrate there, right? But there are other cases in which, so that's going to be a carbon with nothing else attached to it that's electronegative, so that's going to be irreversible. Something that is not on your in your text or in this particular problem set. So this is going to be irreversible. Take an enolate. Okay, so we're going to soon get into excuse me, enolate chemistry. So enolates, again, they're going to resonate back and forth between keto form like you see on the left there and the enol form like you see right there. Right? So in other words, these lone pairs, negative charge is going to kind of sway back and forth between that carbon and that oxygen. Okay, so in effect, you are going to see that that's going to be reversible. Okay, so while that carbon directly does attach or amend to that CO double bond, or about that particular carbon that has its electrons removed from via the oxygen or via that double bond, you're going to see some reversibility. Okay, so that's also in table 17.2. Okay. I made an error. This is actually going to be this is actually going to be reversible. Okay, but I got my wires crossed. This is going to do conjugated addition as opposed to direct addition. Sometimes I have to kind of remind myself of the two, but so in general, most of the reversible reactions that you're going to see are going to happen at the beta position on alpha beta unsaturated ketones, which we'll get into actually right now. So once again, that enolate, just to review, that is going to be reversible. So all these examples that I've given you are reversible. So the ones that are irreversible are going to be, say, some of those hydride reagents, as well as alkylithium, as well as Grignard, as stated before there. Okay, so to wrap things up here, with conjugate versus direct addition, the more polar the actual nucleophile is, the more it's going to tend to go over here where the CO double bond is, or attack right there. Okay. Now, there are two different sites in which things are electron deficient. So one's right here and right here. Okay, so some partial positive charge right there at those two different carbons. So this is going to be the conjugate site, and this is going to be the direct site. So what's really driving all this is where the oxygen is, right? So in other words, if you were to kind of draw a dipole, it's going to go up there in the direction of the oxygen, right? Okay, so in other words, this is kind of a dead zone right here, because if you think of kind of law of averages of where these electrons are flowing up the oxygen, and right there in the middle is pretty much where they're going to be most of the time. Okay. Now, if we have Grignard is going to go direct. Okay, so it's just going to go right here. Then you're going to have a direct addition for your product. Okay. So I'll just put that alcohol there. Remember that you're going to have some RNS. Okay. Number two, or for the second example in the middle, so lithium cuprate is actually going to add things conjugate, because it's going to be a very large species. So in other words, to throw a phenyl ring right there onto that particular CO double bond is going to be a little bit of a stretch. Also, not only is it bulky, but it's also going to be less electronegative than what you're going to see there between that CH3 and that magnesium bromide salt, if you will. So, in other words, this is going to be conjugate addition, that phenyl ring right there. Okay, so that's going to be, again, a matter of R and S there, because, and I deliberately didn't write that stereo center, whether it be, R or S, but just think about it. Also, when you attack right here, or when this pH or that phenyl ring attacks right there as a nuke, what that's going to do is going to bump the electrons up right there. Okay, so what's going to happen is you're going to have this intermediate okay. Now let's say it picks up a proton from this weak acid right here. So you're going to have an enol. But that enol is going to defer to a keto form, right? So proton transfer is going to lead to your keto form. Again. RS. So keto is more stable than the enol counterpart. Okay. So therefore, that is going to be conjugated addition. So this is direct. And then last, this is also going to be direct. Okay. So again, this is going to be a polar salt. And once again, you're going to have a weak acid essentially just protonating that alcohol that would form. So what you're going to get here is one, two, three. So again, direct as opposed to conjugate addition. All right. So take a look at problem 17.60, C and D on page 884, and you'll see, or try to deduce which area you're going to attack, whether you're going to attack conjugate or direct, depending on what kind of nucleophile it is. Okay. And if you have any questions, again, feel free to contact me during office hours. Everyone have a good one. Thanks.